Welcome to AI Paper Podcasts. Today, we're doing a deep dive into a really interesting piece of commentary. It challenges a recent, pretty big claim about large reasoning models.
That's right. Yeah, there's this paper, got a lot of buzz, suggesting LRMs basically hit a wall. They called it accuracy collapse when they try to solve complex planning puzzles, like Tower of Hanoi or river crossing problems.
Right.
The idea was basically beyond a certain size, they just fail completely, almost like it's just an illusion of thinking.
An illusion of thinking, pretty dramatic stuff, isn't it?
It is.
But the source we're looking at today, this commentary, it offers a fundamentally different take. It argues these failures might not be about the model's reasoning limits at all.
Exactly. It suggests maybe the problem is, how the experiments were set up in the first place, artifacts of the design.
So are we really testing the model's ability to think, or just their knack for navigating kind of flawed tests?
That's the big question, isn't it? Are we seeing limitations or just bad benchmarks?
And that's what we want to unpack in this deep dive. Is it the test or the model being tested? We'll dig into the specific evidence this commentary puts forward. But first, here's the quick summary, the 1-minute version for you.
Okay, so a recent study claimed large reasoning models totally fail on planning puzzles like Tower of Hanoi and river crossing once the problems get big enough.
But this commentary argues, hang on, those failures might actually stem from issues with the experiments themselves.
Yeah, like models hitting their output token limits. They just can't write anymore.
Or the automated grading systems misinterpreting what the models are doing, like when a model chooses to cut its answer short.
And this is a big one. They found some of the river crossing problems used in the test were actually mathematically impossible to solve. Like, literally no solution exists.
Oof. Then, the commentary shows some early results where models do solve harder Tower of Hanoi puzzles, but only when they're allowed to give the answer in a different format. Suggests the reasoning ability is there.
Right. So the conclusion is pretty clear. The issues point more towards problems with how we're evaluating these things, not some fundamental collapse in the model's reasoning power.
It's a really significant counter-argument, challenges how we read those results. So let's dive into the details. Their first point is about models hitting constraints, like token limits. What did they notice?
Well, they saw that models often seem, aware of these limits. It's not always just crashing or outputting garbage. Sometimes they explicitly say they're cutting the output short.
Like they know they're running out of space.
Exactly. The commentary mentions examples like a tweet from @scalingz01, where a model working on Tower of Hanoi basically said, the pattern continues, but this is getting too long, so I'll stop here, something like that.
That's fascinating. So it's not necessarily a failure to find the next step in the puzzle.
Right.
It's more like a deliberate choice to stay within the rules, the output limits.
Precisely. And the commentary argues that these rigid, automated evaluation scripts, they totally miss this. If it's just checking for a perfect character-by-character match of the entire expected output,
then any truncation, even if the model announces it, gets marked as a fail.
Yep. Total failure. So the evaluation ends up penalizing the model for being, in a way, smart about managing its output, not for failing the task itself.
A misclassification, basically.
Exactly. And this gets worse because some of these tasks, in the required format, need massive outputs. They bring up the statistics of it, too.
The probability argument.
Yeah, think about it. Even if a model is super accurate, like 99.99% accurate for each token it generates,
okay,
the chance of getting a sequence of, say, 10,000 tokens perfectly right is that probability 0.9999 raised to the power of 10,000, which is actually less than 37%.
Wow, okay, less than 37%, even with almost perfect per token accuracy.
Right. And if the accuracy is just slightly lower, like 0.999 per token, the chance of a perfect 10,000 token sequence plummets to less than 0.005%, almost zero.
So getting a perfect score is almost statistically impossible just because the answer has to be so long and precise, even if the model understands the task perfectly.
That's the point they're making. Attributing these failures only to a reasoning collapse ignores this statistical reality and the model's own coping mechanisms. It might not be about knowing the solution, but about the impossibility of typing it out perfectly in a rigid, verbose format.
Okay, so evaluation flaw number 1, ignoring model awareness of constraints and the statistical challenge of long outputs. What's the next major issue they flagged?
This one's pretty major, especially for the river crossing results. They found out that some of the problems used in the original study, they were impossible, like mathematically unsolvable.
Impossible? Seriously, how did that slip through?
Apparently, the study tested river crossing scenarios, where you have N actors, missionaries, cannibals, whatever, and N was 6 or more. And the boat capacity B was fixed at 3.
Okay, so NO6, B equals 3. That specific combination, it just doesn't work.
Correct. It's actually a known result for these kinds of puzzles, specifically the missionaries and cannibals version. The commentary points to a 2018 paper that proves N greater than 5 with a boat size of 3, no solution exists, period.
Wait, hang on. So the original paper was testing models on problems that cannot be solved, and then marking the models down as failures because they didn't find a non-existent solution.
It certainly looks that way. If you have an automated checker looking for a valid sequence of moves, it won't find one naturally. So it flags it as a failure.
But that's not the model failing to reason. It's the model correctly, implicitly identifying an unsolvable problem.
Exactly. It's like, as the commentary puts it, giving a SAT solver an unsatisfiable formula and then blaming the solver for returning unsatisfiable instead of a variable assignment.
Yeah, that's a perfect analogy. That feels like a really fundamental flaw in the benchmark design itself. You have to check if your questions even have answers.
Absolutely. It really highlights the danger of relying only on programmatic checks without validating the basic properties, like solvability, of your test cases first. This finding alone casts serious doubt on a big chunk of the reported river crossing failures.
Okay, impossible puzzles. That's a huge red flag for any benchmark. Let's shift to Tower of Hanoi. How did the commentary reinterpret the collapse reported there?
Right, so for Tower of Hanoi, the original study saw performance just fall off a cliff after N reached a certain size. The commentary connects this right back to token limits, but specifically how the required output format made it worse.
The output format, how did that play into it?
Okay, so the original study demanded that the model output the entire history of moves at every single step.
Oh, wow. Okay, not just the next move, but the whole sequence up to that point, repeated.
Exactly, which is, incredibly redundant and blows up the token count like crazy. They show it leads to quadratic growth in tokens relative to the number of moves.
Quadratic relative to the moves. And the moves themselves grow exponentially with N. That sounds bad.
It's really bad. Super exponential growth in tokens. The commentary gives a rough formula. Tn is approximately 5 times 2n1 squared, plus some overhead. Tn being total tokens for n disks.
Okay, 5 times the square of the moves.
Yeah. So then they looked at the typical token limits for the models used, like maybe 64,000 tokens for some models, 100,000 for others.
Right.
And they calculated, using that formula, what's the maximum n you could possibly solve if you have to use that super verbose output format, staying within those token limits.
And what did they find? What n does that allow?
Well, for a 64K token limit, you max out around N7, maybe N8. For 100K tokens, maybe N8.
Hold on, N7 or N8? Isn't that exactly where the original paper reported this accuracy collapse happening for Tower of Hanoi?
Precisely. That's the core argument here. The commentary suggests the models weren't failing because their reasoning broke down for N8. They were failing because they literally ran out of space to write the answer in the incredibly inefficient format demanded by the test.
So the collapse wasn't a cognitive limit, it was hitting the physical output buffer size.
Exactly. It wasn't about knowing the answer. It was about whether the answer, written in that specific way, could even fit.
That makes so much sense. It reframes the failure completely. It's not a thinking problem, it's a typing too much problem.
Right. And that leads directly into their next point, which is kind of the proof in the pudding.
Which is, if you change the output requirement, if you let them type less,
then they can solve the harder problems.
Yeah.
If the failure was just the format, a better format should fix it.
Right.
So they ran a quick experiment.
What did they try?
They took a much bigger Tower of Hanoi problem, N15. Now, N15 requires over 32,000 moves. Writing that out step by step with history. Forget it. Way beyond any token limit.
Okay, so N15. What did they ask the models to do instead?
Instead of the move list, they asked the models to generate a simple Lua function, a piece of code that, if you ran it, would print the correct sequence of moves.
Ah, so generate the algorithm itself in code, not the massive output of the algorithm.
Exactly. This tests if the model understands the underlying recursive logic and can express it compactly.
Clever. And did it work? What were the results?
They tested several top models: Claude 3.7 Sonnet, Opus 4, OpenAI o3, Gemini 2.5, and they got very high accuracy across the board. The models successfully generated the correct Lua code for N15.
N15 solved. The problem size considered way beyond the collapse point.
Solved. And here's the kicker. They did it using fewer than 5,000 tokens, sometimes much fewer.
Wow. Less than 5,000 tokens to effectively solve N15 by writing the code. versus hitting a wall at n and 8 because the explicit move list needed 64,000 tokens.
That's the stark contrast. It strongly suggests the models did possess the reasoning capability for N15 all along. The failure wasn't in understanding the recursion, it was purely an artifact of the incredibly burdensome output format required by the original evaluation.
That's really compelling. It clearly separates the reasoning part from the output generation part.
Absolutely. It shows how much the representation matters in these evaluations. It's not just a minor detail.
Okay, so we've got awareness of limits, impossible puzzles, token limits driven by format, and success with alternative representations. What was the final piece of their critique?
The last major point was about how complexity itself was measured in the original paper. They used something called compositional depth, which was basically just the minimum number of moves needed for the solution.
Which, okay, seems intuitive again. More steps equals harder problem.
Well, the commentary argues that's potentially misleading. It confuses the length of the solution path with the actual computational difficulty of finding that path. They use a table 1 in their paper, to make this point really clear by comparing different puzzles.
Right, let's break that comparison down. Tower of Hanoi first.
Okay, Tower of Hanoi, TOH. As we said, exponential moves 2 and 1. Looks super complex by the number of moves metric for large N.
Yeah.
But finding the next move in the standard 2H algorithm is computationally trivial. An O1 decision, basically. The branching factor, how many choices you have, is effectively 1 if you follow the algorithm. There's no real search involved.
So very long path, but each step is easy, no searching needed. Got it.
Right. Now, contrast that with river crossing. Way fewer moves, maybe around 4n. Looks much simpler by the number of moves metric.
Okay.
The branching factor is much higher, maybe 4 choices at each step. And crucially, finding a valid sequence involves satisfying tricky constraints. Don't leave the missionaries outnumbered. This often requires actual search through possibilities. It's known to be NP hard.
NP hard, meaning potentially exponential time to find the solution because you might have to explore many paths, much harder computationally than just following a simple rule.
Exactly. The difficulty is in the search and constraint checking, not the path length. And then there's blocks world. Even fewer moves, maybe 2n. But the branching factor can be huge, like ON squared. And again, finding a plan requires complex search. It's PS-based complete.
PS-based complete, generally considered even harder than NP hard. More complex planning and potentially larger search spaces.
Correct. So the commentary's point is, just because Tower of Hanoi has an exponentially long solution doesn't mean it's computationally harder for the model in terms of the reasoning needed per step, compared to river crossing or blocks world, which require complex search and constraint satisfaction despite having shorter solutions.
The real complexity for the LRM might lie in the search or constraint satisfaction, not just how many steps are in the final answer.
Precisely. That minimum moves metric used originally was misleading. This helps explain why models might ace the algorithm for a huge 2H problem, but struggle with a shorter river crossing problem, because the river crossing problem demands a much harder kind of computation, like search.
Okay, that really ties it all together. Let's recap the argument. Models know about output limits. The benchmark had impossible problems. The 2H collapse matches token limits from a bad format. Models work fine with better formats. And the complexity metric was flawed.
Exactly. They argue that taken together, these points strongly suggest the original paper's accuracy collapse and illusion of thinking are much better explained as artifacts of poor evaluation design and misinterpretations, rather than some fundamental breakdown in LRM reasoning.
So it sounds like they're basically saying the illusion of thinking was more like an illusion created by the test setup.
That's a very good way to put it, yes.
So for you listening, maybe you're an AI researcher, an ML engineer, why is this kind of deep dive into benchmark methodology so important? Why should you care?
Oh, it's absolutely critical, because how we measure these models, how we evaluate them, fundamentally shapes our understanding of what they can and can't do.
Right.
If the benchmarks are flawed, if they penalize models unfairly for hitting limits, or use impossible tasks, or measure complexity turly, then we get a distorted picture. We might think models are less capable than they are, or maybe even more capable in the wrong ways. It affects research directions, deployment decisions, everything.
It really hammers home the need for incredibly careful and thoughtful evaluation design. And the authors here, they don't just criticize, they offer concrete suggestions for improvement, right?
They do. They lay out 4 key recommendations for anyone working on evaluating LRMs, especially on reasoning and planning.
Okay, what are they?
1. Design your tests to carefully separate the model's core reasoning ability from practical things like output limits.
Right,
Don't conflate them.
Makes sense, too.
2. Always verify that your puzzle instances are actually solvable before you use them to test models. Basic sanity check.
You'd think. Okay, 3.
3. Use complexity metrics that actually reflect the computational difficulty, things like search depth, constraint complexity, not just the length of the final solution.
Right, measure the hard part. And 4.
4. Consider using multiple ways for the model to give the answer, like asking for an algorithm or code, not just the step-by-step output. This helps distinguish understanding the logic from just executing a long sequence.
Those sound like really solid principles for building better, more reliable benchmarks. It's not just about automating tests, it's about making sure the tests actually measure the right thing.
Exactly. Building evaluations that reveal capability, not hide it behind artifacts.
And they wrap up the commentary with a really pointed question, kind of a mic drop moment that sums it all up.
Yeah, it's a great closing line. Based on everything they've shown, they leave you with this thought. The question isn't whether LRMs can reason, but whether our evaluations can distinguish reasoning from typing.
Whether our evaluations can distinguish reasoning from typing.
Wow, that really cuts to the heart of it, doesn't it? Are we testing intelligence, or just the ability to generate a long string of characters under potentially flawed constraints? Definitely gives you something to think about next time you see benchmark results claiming models can or can't do something.